We're just going to go through a little more clarification on systems of equations, matrices, and their inverses. So like if we had a system of equations here, I just kind of made one up here. When we're solving the system of equations, we use things like substitution and elimination. So like for instance, if I was approaching this one, maybe I would notice right away that like the y's could cancel. So like what I could do is I could simply take these two equations and like subtract them and create this new equation that I could use in my system. And like once I get that equation, like I'm thinking, okay, well if 2x plus 2y is equal to 8, and I know that x and no y's is equal to 5. Well, this is a new system, right? And this new system is still going to give me the same answers. I've used my first original equation, and I used this new one that I got by combining another one. Now, when I think about systems of equations, like if I wrote this one, all I did was change the variables from a's to b's, or from x's to a's and y's to b's. I wouldn't do anything different to solve it, right? Like let's say I wanted to use elimination. I'd really just look at the coefficients and, oh, well, they're not the same. So maybe I can multiply the first one by 5 and I could multiply the second equation by 6. Sorry, that's supposed to be a 30. And then maybe I can just subtract them, right? So what I'm getting at with the system of equations is when we are solving them, we really don't care what letters were used to write that, which is why we start to think about a system of equation as like, well, all I really need is to know the coefficients. The variables that were used, like in this case, x and y, aren't really that important. So I want to get this conceptually in your head that I kind of separate the coefficients from what letters were used. But this is our main understanding that I can take a system of equations and represent it as a multiplication of matrices. Let's just check our work here, right? This is a 2 by 2 matrix, and this is a 2 by 1. So we know that the insides match. So the resulting matrix is going to be a 2 by 1, which means there's two elements, one in the first row and one in the second row. So if I thought about multiplying these to get my answer, I'll kind of write it in two ways, show my work, and then the final answer on the right. If I wanted to get this first element, I would take the first row and the first column, because this is row 1, column 1. So I'd multiply 6x, and I would add 2y, and that would be this first element there. And on the bottom, if I wanted the second element, which is in row 2, column 1, I would take row 2 and multiply it by column 1, which would give me 5x plus 2y. Or in other words, when I multiply these matrices together, I get the original systems of equations. So if this thing in element 1, row 1, column 1 is supposed to be the same as this, well, we know that this element is 8. So I could say this was 8, and then likewise, that bottom element should be 3. So what we can do is we can take a system of equations and we can write it using matrices. Now that's important because the next part of this is in general what we've done is we've created this matrix. One of them holds our coefficients, one of them holds our variables, which I'm abbreviating, and one of them holds the answers. Now let's just use symbols for our matrices. Let's say I call this matrix A. Let's say I call this matrix X just because it's like a variable, and I'll call this matrix B. Well, when I'm solving a system of equations, what I want to know is what is the value of x and y. So in other words, I somehow want to get this matrix, which I've called matrix X, all alone. Because if I know what the elements in matrix X are, if I know what's here and I know what's here, well, then I know which one of them is X and which one of them is Y, right? Because that's what we said. Our matrix X holds the value of X and the value of Y. So what I need to think about then is how could I take the statement that I have up top and turn it into this one? Well, what I notice is the only difference is I don't want the multiplication of A. So I need to get rid of matrix A on the left side. We don't have division of matrices, but we do know a fact that if I were to take the inverse of a matrix A and multiply it by another matrix, or itself, excuse me, a matrix times its inverse is always the identity. And I'm just going to write that identity as I for a second. And then I also know, just carrying down my work, that a matrix times the identity is always just itself. So what I found out I could do on the left side, if I multiplied by the inverse of A, I was able to undo the matrix A, and I'm just left with the matrix I'm looking for. So we know that when we solve equations, what I do to the left side, I have to do to the right. Now, the only thing that's weird with matrix multiplication is we know the order matters. For instance, the matrix A times the matrix B is not the same as the matrix B times the matrix A. So in other words, the order of multiplication in matrices is important. So on the left side, I multiplied A inverse on the left of that statement. So I have to make sure to do that over here. I have to multiply the left side of the statement. But if we carry down that work, what we would then know is on the right side, our matrix X is going to be the same thing as the inverse of A times the answer matrix. And that's going to be our clue to solving this system. If I know what matrix A is, I can find its inverse and multiply its inverse by the answer matrix. And that's what we have symbolically right here. So we're going to go through one example of doing that. So I just have our original system of equations that's now written as a multiplication of matrices. We'll relabel this is A, this is our answer matrix, and then we're just going to call this matrix B. So I need to find the inverse of A, and the way that we find the inverse is we take that matrix and we augment it. In other words, we just attach it to the identity matrix. And I like this moment to remind myself of why I connect it with the identity matrix. Wouldn't these two equations be the ones that we want? I wish I could have an equation. I'll just kind of write it somewhere else. If my equation was just 1x plus 0y equals a number and 0x's plus 1y equals a number, I would be done solving my system because I know x would be this and y would be that. So that's what I wish my system would look like. So that's why I augment it with that identity matrix. So what we're going to do now is we're just going to we're going to perform row operations to find our inverse. So we always start by turning this into a 1. Want to get the 1 in this column, use the 1 to get a 0. Then we'll move on to column 2. We'll get the 1 here, and then use that to get a 0. So I'm only working on my first row right now, so I'm not changing my second row. So I'm just going to put that back. What I'm going to do is rewrite the first row with an equivalent fact. I'm going to take the first row and just multiply it by 1/6. Like we know if I take an equation and multiply both sides by a constant, it's still a true equation. So I'm going to replace my equation in row 1 with this new equation. So when I multiply it by 1/6, I would get 1, 1/3, 1/6, and 0. So now we're getting closer to what we want. We wanted our matrix to look like this. Right now we have a 1 in the place that we wanted to. So once I have a 1, the way that I would create the 0 below it is by adding equations together, just like we were doing in our warm-up, right? I can add equations together to create a new equation. Once I get that new equation, I can use that equation in my system. So if I want to get this number right here to be a 0, I'm going to need to add -5 to it. So what I'm thinking about then is if I took the equation in row 1 and multiplied it by -5, I would get those coefficients to be opposites. So if I took that first row and multiplied it by -5, I would get -5 minus 5/3. This would turn into -5/6, and that would still be 0. Now, if I add that to the original second row, right, if I add an equation to another equation like we do in elimination, so here I'll add them, 5 and -5. I've already taken care of these fractions ahead of time, and you could use your calculator, but this will be 1/3. This will be -5/6, and that'll be 1. Just like I set up here, if I combine two equations to make a third equation, I can use that third equation in my system, and that's what I'm going to do here. So I'm going to use that result as my new row number 2. So I didn't change my first row because I liked that it had a 1 there. But instead of the second row, I wrote a different equation, and I'm going to use that one instead. Okay, so we're getting closer. We have the 1 in the upper left and the 0 in the lower left. Now we need this 1/3 to be a 1. So when I'm trying to get a 1, all I need to do is multiply a row by something. So for example, if I wanted to change this equation so it didn't have a fraction in it, I could simply multiply everything by 3, and it's still true. And that's what I'm going to do here. I like my first row. I'm going to keep that. But instead of my second row, I'm going to define a new equation to work with. What I'm going to do is I'm going to take what's in my second row and simply multiply it by 3. And that's going to be my new second row. So 0, 1. Now 5/6 times 3 will give you, sorry, let me multiply that. So that's negative 15 over 6, which is really negative 5 over 2. And then this turns into a 3. Okay, so now I'm almost done. All I need to do is turn this into a 1. And the way that, turn this into a 0. And the way I get 0 is just through addition and subtraction. So I would need to add negative 1/3 to this. Or in other words, like we were saying, if I wanted these equations to cancel out, I need to add opposites. So if I want to cancel out negative 1/3, what I think I could do is I could take what's currently in the second row and multiply it by negative 1/3. So I'd get 0, negative 1/3. And then when I take 5/2 and multiply it by negative 1/3, I get 5/6. And then I would get negative 1. So that's just me taking this equation and just multiplying it by a constant. So then I can add the original equation in row 1. Like I'm going to use the linear combination. I'm going to combine these equations to make my new equation. And I'm just going to put that equation in row 1. So I didn't change my second row, but I'm using that equation or that fact to write a new fact for my first row. And that's going to be a 1, a 0, a 1, and a negative 1. So that's my new fact. So what we've done is we've successfully found the inverse of matrix A, because this is now the identity. So the inverse of matrix A is now this, 1, negative 1, negative 5/2, and 3. Now the reason we wanted that inverse matrix is because conceptually we knew if I could find the inverse of that matrix, that would help me isolate the answer matrix. So to get the matrix that contains the value of x and y, all I need to do is multiply matrix B by the inverse of A on the left. So we know what matrix B is, and I know what my inverse is. So if I took matrix B and multiplied it on the left, by matrix A, according to our understanding, that should give us matrix X, which is, again, I'm just going to say, what is matrix X really? It's a capital X. So matrix X is really made up of the value of X and the value of Y. So if I want to figure out what X was, which is in row 1, column 1, I would take row 1 and multiply it by column 1. So I would get 1 times 8 plus negative 1 times 3. Whatever that works out to be, that's in row 1, column 1. So that's the value of X. If I wanted to figure out the value of Y, which is in row 2, column 2, I would take row 2 and this is in row 2, column 1. I would take row 2 and multiply it by column 1. So I'd take negative 5/2 times 8, and I would add 3 times 3. So if I just reduce the matrix on the left, I know whatever's up on top is going to be the value of X, and whatever's on the bottom is going to be the value of Y. So when I look at what's on top of the matrix, well, 1 minus 3 is 5. This is going to be negative 40 divided by 2, which is negative 20, plus 9 is negative 11. So I've now shown, using matrix operations, that 5 is equal to X and negative 11 is equal to Y.